All right, welcome ladies and gentlemen. This is the final video in our atomic theory unit. It's video number 8, so you got to make sure that you have your note packet open to where it says video number 8, and I think that's all we're going to need for that one. And this one is on the quantum mechanical model of the atom, which is the modern model. It's the one that we still use, specifically about what I like to call the organizational structure of the quantum mechanical model. So our goal for this is to be able to describe the layers, especially compare and contrast how these layers of the quantum mechanical model are different from Bohr's model, and some things that are the same between them. The compare and contrast is a big thing. So first up, the quantum mechanical model, our modern model of the atom, the big two guys who went into developing it were Schrödinger and Heisenberg. And this is also sometimes called the modern model, the orbital model, or the wavelength mechanical model. Regents really likes wave mechanical model, which is sort of a variation of this one, but know that really any references, it's essentially referring to this one. I like to call it the quantum mechanical model because it is in fact based on quantum mechanics, because electrons obey the laws of quantum mechanics because electrons are weird. They do weird stuff. So the first thing, the first big thing that makes the quantum mechanical model different from Bohr is something that we've discussed before, but it's worth mentioning again. In this model, we cannot know exactly where electrons are. Electrons are not found on exact paths. We bring in this idea of probability and uncertainty. We can only know the most probable location of an electron. We cannot know exactly where an electron is. And this is a huge shift from Bohr, because Bohr's like, of course you can know where they are. They're on orbits, duh. And the quantum mechanical model is like, no, you can't. You can't know where they are. You can know to a reasonably high probability where they are, but you can't know exactly where they are. So this idea of uncertainty, this idea of probability, it's a mathematical model. It's very complex, but that's a big difference between them. So orbital is the word that we use to describe this area where we think an electron most likely is. Regional space where it's highly likely to find an electron. The probabilistics come in at 90%. Basically, if an area of space, if there's 90% or greater chance of finding an electron there, we call that an orbital. But there is a cutoff, so it's like it's not 100%, it's 90% or better. We know to within 90% or better that we can find an electron there. Region of space where it's highly likely to find an electron, also called an electron cloud. But again, you can't know for sure where it is. We do not know with certainty where it is. So it's not orbits anymore, because an orbit implies simply a circular path. It is not a circular path. It is a fuzzy cloud of probability. We do not know exactly where it is. It is an orbital. It is not an orbit. It's unfortunate the words are so similar because they mean very, very different things. Ooh, one huge key point about this is that an orbital can fit a maximum of 2 electrons. Orbital can only hold 2 electrons. So when we're talking about this region of space where it's highly likely to find an electron, it's possible that it could be a region of space where it's highly likely to find 2 electrons. There might only be 1 electron there, and it might even be an empty space, but you cannot put 3 electrons within the same orbital. So it maxes out at 2 electrons per orbital. Now, the quantum mechanical model organization. I'm going to run down this fairly quickly in the video, and I will say right now, if at any point you feel confused, that's okay. We're going to talk about it in class. I've got a model for us to look at, so it's okay if during this video you're kind of like, huh, I actually expect it. So the organization to the quantum mechanical model is a lot more in-depth than Bohr, because Bohr just had its energy shells. Well, we still have electron energy shells in the quantum mechanical model. However, within the electron energy shells, the shells contain subshells. So you break down a shell to see that there's actually more to it. It's not just the one shell. There's actually smaller things within the shells. Oh, and then guess what? Within the subshells, that's where we have the orbitals, the regions of space where it's highly likely to find an electron. And within the orbitals, we have the electrons themselves. So kind of the way I like to think of it is almost like this would be a Venn diagram. By the way, this is not a picture of an atom. This is a Venn diagram describing this. So electrons are at the center, and electrons are found inside orbitals. So it's this idea that the orbitals contain the electrons, because they do. That's what orbitals do. And where are the orbitals? The orbitals are within the subshells. And where the subshells are within the energy shells. So this nice little, this Venn diagram idea. So you have your electron energy shell. Within that, you have subshells. Within the subshells, you have orbitals. Within the orbitals, you have electrons. And that's what I mean by the organizational system. But of course, there's more to it than just this. There are rules to all of these things. There are rules to subshells and rules to orbitals and what subshells and how many subshells each thing can have. So we're going to run through that as well. But this is the idea about what of subshells. What does this really mean? So Bohr's model, which is really commonly used because it's easy. Bohr's model is pretty easy. We just have the shells and that's it. But now with the quantum mechanical model, we can break the shells down further. So there's more to it than just shell 1, shell 2, shell 3. We still have shell 1 here, right close to the nucleus, but then notice that shell 2 is broken down a little bit more. The 8 electrons that are in shell 2, they're not evenly spread out, and that's significant for us. So going through each of these levels of organization, the shell, the subshell, the orbitals, etc. The first level of organization is the principal energy shell. And this is what is called the principal quantum number. And this is actually n. Now this is a nice place to start because this is the exact same n that Bohr talked about, where n equals 1 is the first shell, n equals 2 is the second shell. So literally that aspect is identical. Bohr had electron energy shells. The quantum mechanical model has electron energy shells, and they use the same nomenclature for each thing. So n equals 1, n equals 2, etc. It's identical. It means the same thing. But now, within the subshell, we break n down a little bit further within the energy shell, we break it further down into the subshells. And this is not like Bohr. So each principal energy shell is divided into subshells. The subshells have names. The names are weird. The names for the subshells are called S, T, D, and F. And there is a quantum mechanical reason for why they are these particular letters. And they're lowercase. They have to be lowercase, not uppercase. But those are the names for the subshells. Now, these subshells, I've actually given them to you in order in terms of energy and in terms of location. So S is the lowest energy subshell out of the 4, then comes P, then comes D, then comes F, which means that S is, in a given energy shell, S would always be the one that's closest to the nucleus because it's lowest in energy, and in a given energy shell, F would be the one that would be farthest away from the nucleus. It would be highest in energy. So notice that this idea of being lower energy and closer to the nucleus is also identical to Bohr's idea of lower in energy means closer to the nucleus. Now, each energy shell has a different number of subshells. So you don't have S, P, D, and F in all of your energy shells. There is, however, a predictable way to tell how many subshells each energy shell will have. The first energy shell, so n equals 1, so our first energy level, will have 1 subshell. First shell has only 1 subshell. Now, which of the SP, D, or F subshells will it have? It's going to have the lowest energy one first. So in the first energy shell, there is only an S subshell. The second energy shell, n equals 2, has, wait for it, 2 subshells. Oh my gosh, the energy level 1 has 1 and energy level 2 has 2 subshells. So which subshells will it have? It will have the 2 lowest energy subshells. So it's going to have S because that's lowest in energy, but then it needs a second one, so it's going to add on the P. It has an S and a P subshell. Ooh, how many subshells do you think 3 has? Oh, are we possibly sensing a pattern? Because there is a pattern here. The third energy shell has 3 subshells. Give yourself a pat on the back if you anticipated that. And the pattern is indeed for every n energy shell, it will have n subshells. So shell 3 has got 3 subshells. What 3 subshells will it have? It will have an S, a P, and a D. So that means that we do not see a D subshell until we get to the third energy shell, whereas we see an S subshell within the very first shell. And the fourth energy shell, n equals 4, is going to have, are you totally shocked? 4 subshells. Oh my God, never saw that one coming. Right, 4 subshells in the 4th shell, and they're going to have the 4 lowest energy ones. So in this case, they are going to have an S, P, D, and an F. There are hypothetical, theoretical further subshells like G and H, and they start going alphabetically like that. But we haven't found an atom that actually has those occupied yet, because we just run out of electrons, things get placed. So that's this, each shell has n number of subshells, and they kind of go in that order in terms of which subshells they have. And then S, P, D, and F, there's more that we can say about those, because S, P, D, and F, each subshell has a certain number of orbitals, areas of space where we can find an electron, or it's highly likely that we'll find an electron. So this is big too, because there's a cap. Each subshell can only fit a certain number of electrons based on the number of orbitals. Now remember, this is super big. Each orbital can only hold up to 2 electrons maximum. So, our subshells, S, P, D, and F. We're going to start with S because that's our lowest energy one. The S subshell can only hold 1 orbital. Now remember, for each orbital can hold up to 2 electrons. So how many electrons can that can an S subshell hold? 2, because each orbital, right, can hold 2 electrons maximum. So that means that the S subshell can hold a maximum of 2 electrons because it only has 1 orbital. And every time you see an S, whether it's the S that's in the 1st energy shell or the 3rd energy shell, it's still only going to have 1 orbital. P, on the other hand, can hold 3 orbitals. 3 orbitals fit within P. Now remember, an orbital can hold 2 electrons, which means the total number of electrons that can fit in a P subshell is going to be 6. Then D. D can hold, the D subshell contains 5 orbitals. We might be noticing a pattern here. The D subshell can hold 5 orbitals. If you multiply that value by 2, because each orbital contains can contain up to 2 electrons, that means that the D subshell can hold 10 electrons total. And then, can we make a guess how many orbitals fit within the F subshell? If you guessed 7, then you have been paying attention. Yes, we are in fact going up by 2s, so we're going by odds. And 7 orbitals within the F subshell, 2 electrons per orbital, so we double that number to get the number of electrons. 14 electrons total fit within the F subshell. If you're confused, that's normal. That's totally normal. And tomorrow or the next day in class, we are going to work with this. We're going to practice with this, so hopefully this organizational system starts to make some sense.